and welcome back to Polar and Nonpolar Bonds. Now it's time to tackle our next big question, which is on molecular geometry. But I would like you to take a moment first and pause this video and make sure you have a ruler, a piece of paper, maybe 2 or 3, and definitely several colors of pens or pencils, because this one you're gonna have to color code. So I'll just give you a moment and then we will move forward. So our big question is, how do you predict the geometry and the shape of the molecules? And we're going to get to that in just 1 second. This is the time to have a sheet of notes out in front of you because we're going to do some definition and important information first. And then we're going to go ahead and build our chart of information on shapes. When we're talking about the VSEPR model, it stands for Valence Shell Electron Pair Repulsion Model. And this is based on the arrangement that minimizes the repulsion of a shared and unshared pairs of electrons around the central atom. Let's remember that electrons are negative, and it's like having 2 negative magnets by each other. They don't want to be by each other, so these electrons and shared pairs of electrons arrange themselves in space in a 3D way that gets them as far away as they could potentially can be from the other electrons. Another really important part of the VSEPR model is the bond angle. This is the angle formed by any 2 terminal meaning ending atoms, and the central atom. So it takes 3 atoms to make a bond angle. These are predicted by the VSEPR model, are supported by lots and lots of experimental evidence. So we know these are the actual shapes that atoms and molecules take in a 3D way in the actual world. Now remember, lone pairs will have a slightly larger orbit than the shared electrons. So now is the time to take a moment, pause the video, write down this important information so that when we look at the different information on a chart, you can go ahead and be ready for that. Okay, now you're going to make your chart, and you can pause the video to make sure that you have enough. It goes over several slides, so you're going to want to make sure you have plenty of room on your page. On your first column, you're going to write total pairs, then you're going to write shared pairs in your second column, lone pairs in your third column, the molecular shape name in your fourth column, your molecular shape in your fifth column, and then go ahead and write bond angle in your sixth column. Okay, let's walk through this. An element with 2 total pairs and 2 shared pairs with no lone pairs is linear. It's going to have a very flat, straight molecular shape, and you can do this also in your Lewis structure, and it's going to have a bond angle of 180 degrees. If you have an element with 3 total pairs and 3 shared pairs, it's going to be called a trigonal planar, and it's kind of going to look like a little V with a straight line on top, and the bond angle is going to be 120 degrees. If you have 4 total pairs and 4 shared pairs, and again, we don't have any lone pairs yet, it's going to be tetrahedral. And it's going to have a bond angle of 109.5 degrees, and it's going to kind of look like it's sitting on a tripod with something straight sticking up. Now we're starting to get to some of those with lone pairs. You're going to have 4 total pairs with 3 shared pairs and a lone pair, and it's going to be trigonal pyramidal. Now if you're looking at the molecular shape and you see kind of dots going along, that means it's going to go behind. It's like a 3D type of angle. And you can see that fin on top with a lone pair. It's going to take a slightly larger orbit, and it's a bond angle of 107.3 degrees. If we have 4 total pairs, 2 shared pairs, and 2 lone pairs, it's going to be a bent molecular shape with a bond angle of 104.5 degrees. Now, we're getting pretty big elements now, but if you have 5 total pairs and 5 shared pairs, which would be almost a expanded octet, you're going to be trigonal bipyramidal. If we're measuring the angle from vertical to horizontal, it's going to be 90 degrees. And if you're measuring it from horizontal to horizontal, that is 109.5 degrees. And finally, if you have 6 total pairs and 6 shared pairs, you're going to have an octahedral where everything is 90 degrees from each other measured from the central atom. Okay, I'll give you a moment to digest this, think about it, go ahead and pause the video and just go, phew, I got this thing written down. Okay, let's take a moment to talk about how orbitals can share electrons. It's in a process called hybridization. This is a process in which atomic orbitals are mixed together to form new identical hybrid orbitals. Each hybrid orbital will contain one electron to be shared with another atom. Lone pairs may also occupy hybrid orbitals depending on if it's a lone pair that is being shared or offered from different items, or if it's from, for example, this electron structure here, the orbital is being supported by the hydrogens. Thank you very much. This is important to know, and I appreciate you listening.